let's take a look at phase diagrams. So I feel like phase diagrams look intimidating. They look really abstract. That's what I have up right here is a phase diagram for, I think this is for water. It doesn't really matter. But it's just a bunch of lines on a graph. It feels really abstract. But once you look at them for a little while, they're not that bad. So along the y-axis over here, or the vertical axis, we have pressure, and then along the horizontal axis down here, we have temperature. And then we see these lines sort of drawn on here, and there's some markings on there as well, and we can talk about what those all mean. But so really what we have, though, is pressure plotted as a function of temperature. And what the lines that are on here indicate, these are the boundaries for phase transitions for a particular substance. So as I cross over, say, for example, from here to here, like let's say I was at whatever this pressure is here, and I keep the pressure constant, but I increase the temperature, so from about 180 to 290 Kelvin, I will go from one phase of a substance to another phase of the substance. And that's basically the entirety of these things, is as you change the pressure, so you move this way. So like if I, let me erase that for a second. If I, let me get rid of these green lines as well. So let's say I'm just looking at this. So you can see that like at different pressures, so if I'm at 1 Pascal, the phase transition happens at a particular temperature, maybe like right around 200 Kelvin. But if I increase the pressure to whatever this is 10 to the third, so 1,000 pascals, must be logarithmic or something over here. But if I increase it to 1,000 pascals, now the same phase transition, is going to take place at a higher temperature, maybe somewhere closer to 275 Kelvin. Okay, so that's how you read these, or that's how you'd want to read them. The other important thing is to actually know what phases you're going between. So this is a very sparsely labeled diagram, but S here is referring to solid, and let's see, L is going to be referring to liquid, and then V is going to be referring to gas. I don't know why they chose V for gas. This refers to the triple point, and this to the critical point, and those are just two special temperature pressure intersections, and we'll talk about those in a minute. But let's look at the actual phase transitions that we can go through and make sure that all makes sense to us. So if we think about the absolute extreme on this graph, we can look right here at this corner. So when the temperature is close to absolute zero, well, actually, let's look at things that reinforce each other. So let's look at this. So maybe like right here. So when the temperature is close to absolute zero and the pressure is extremely high, you can think about what you might expect the phase to be. Right? So when things are cold, what do things tend to be at cold temperatures? Think about water. It tends to be ice. And then what do high pressures favor as well? If you think about things in a vacuum, they tend to evaporate. High pressures tend to favor solids. So at the absolute highest pressure and the absolute lowest temperature that you could have, at least on this graph, we are not surprised that this is a solid. As we move to higher temperatures, so as I, let's say, take this, let's say I stay at the same pressure, so really high pressure, whatever that is, 10 to the 6, and now I start moving out, for a while, as I increase the temperature, nothing really happens. Sure, I'm increasing the kinetic energy of the system because I'm increasing the temperature, but things don't really start to get interesting until I break over the the phase transition line. And so I can take and look at this temperature. So now I'm crossing over this phase transition line, and I can say, okay, well, what temperature does that phase transition take place at? It takes place around right here at 250 Kelvin. So if I go between, if I go between, if I'm at some scene pressure, 10 to the 6 pascals or something like that, and I increase the temperature to right around 250 Kelvin. So this is definitely not water. What I end up with, because 250 Kelvin's around 20 degrees Celsius, minus 20 degrees Celsius. But what I end up getting is a solid to liquid transition. Okay, so right here, the solid to liquid transition takes place at about 250 Kelvin. As I move down this phase transition line, you can see it changes a little bit. So if I were, let's say, at this pressure instead, and I started increasing the temperature, the phase transition would actually happen a little bit later. So a little bit higher of a temperature. A little bit higher of a temperature to go from solid to liquid. If I continue to drop the pressure down, let's say now I'm right here at 1 Pascal. Let me change colors for this. So now I'm at 1 Pascal. Now I go through a phase transition eventually when I increase the temperature as I move to the right, as I would expect, because I'm at a solid. As the temperature gets hotter, I expect it to go from a solid to a liquid or a solid to a gas, because I'm increasing the kinetic energy, and then ultimately I'm going to be putting enough heat to where I can start to break those bonds in there. What's interesting about this phase diagram, though, is it shows you that at high pressures, you go from solid to liquid, but at lower pressures, you can go from a solid directly to a gas. Okay? So we've got a phase transition here as well, but what's happening there, this is sublimation, where you're going immediately from a solid to a gas. Excuse me. This might be for carbon dioxide. That might be what this phase diagram's for. So if you're familiar with dry ice, which is called dry ice because it goes from a solid immediately to a gas, it doesn't ever get wet. It's because the phase transition happens for solid carbon dioxide, which is what dry ice is. The phase transition where you go from a solid to a gas actually happens at atmospheric pressure and room temperature. For water, which is the thing we're most familiar with, there the phase transition at atmospheric pressure takes place. It goes, we're familiar with, which is solid to a liquid and then to a gas. But you can see if this is indeed carbon dioxide, if we lived on a different planet where the atmospheric pressure was significantly higher, that indeed carbon dioxide could also go through a solid and then through a liquid. So it could break through this, what I've colored green here, this phase transition, become a liquid, and then keep going to become a gas in the way that we're sort of familiar with. So we can do gas in this pink color. In the way that we're familiar with liquid water, right? So dry ice or phase transitions can take place where you go from a solid to a liquid or gas, or you can go from a solid to gas. It's really dependent on the pressure of the system. But mainly when you're reading these types of phase diagrams, all you're doing is you're looking at a particular pressure and temperature, and you can either say, so if I'm looking at, let's say I'm at this pressure here, so 10 to the 5th, and I'm at a temperature of 400 degrees Celsius, I can immediately say what phase I'm going to be in. I picked kind of a weird one because it's very close to the phase transition. But here I'd be as a gas, Or if I was at 500 degrees and 10 to the 3rd, what would I be? Again, I'd be a gas. So that's one way to do it, is like you take the sort of the coordinates for it of the pressure and the temperature, and you can figure out what phase a particular substance is going to be in. The other useful thing is kind of what I started out on, which is just that you can sort of say what will happen if you're at constant pressure. You can say what phase transition you'll even see. So it's the intuition from just our experience with water is that the phase transition will always be solid to liquid to gas, but that's not always true. Even for liquid water, there are pressures where you will sublime it or sublimate it or whatever. There are pressures where you'll sublimate it, even though that's not kind of what we're familiar at. So if you, for example, if you cool ice down really, really cold and put the pressure really, really low, you can actually go immediately from a solid to a gas. And that's kind of what we see here. So at lower pressures, you tend to see sublimation from solid going to a gas. And at higher pressures, you tend to go through the liquid state. And so for water, it just happens that we're in the sweet spot on Earth where we go from a water to a liquid to gas. But on other planets, it might just go immediately from water to gas. Yeah, so that's basically it for phase diagrams in terms of just being able to read them. So you'd want to be able to, let me get rid of some of this writing on here. So you want to be able to, one, for a given temperature and pressure, be able to say what the state is of a particular substance given the phase diagram, regardless of whether it's labeled or not. It's always going to be solid over here, liquid up here, and then gas down here. And then the other thing that you need to know is that if you're given a particular pressure, for example, then you should know that whether or not, if I increase the temperature, is it going to go through from a solid to a gas or a solid to a liquid? So you need to be able to kind of like follow what would happen as you change one of the variables. The last thing is, what are these two things? So TP on this chart is the triple point. And this is just where all three phases can exist. So the triple point is where three phases can exist simultaneously. So yeah, so for this particular substance, that's at 1,000 pascals. And looks like maybe room temperature. 273-ish Kelvin. The other point on here that we see is, the other point that we see on here is C sub P or CP. So not to be confused with the heat capacity. Yeah, what is CP? So CP is the critical point. We're not super worried about this, but once you get above this, you notice like here, this dotted line. Once you get above the critical point, the way we define phases doesn't really make as much sense. So this is like somewhere in between a gas and a liquid. So the fluid becomes what's called a supercritical fluid, and it's got properties that are somewhere in between a gas and a liquid. And this is like more common. It's not as exotic as it sounds. So like a really common place where you see supercritical fluids being used are in extractions. So if you get like like the marijuana industry in California and other states where it's legal, the way that they extract out the THC and cannabidiol and all those different types of things is they will use supercritical carbon dioxide. So they'll get the temperature really high and they'll get the pressure really high, and you get this you get carbon dioxide. It behaves sort of like a fluid, sort of like a liquid, and sort of like a gas. And the advantage of that is when you do the extraction, it pulls out all the molecules, like it extracts them out into the supercritical fluid, and then all you have to do to get the extract out, whatever you're trying to, the cannabidiol or whatever the plant extract is you're looking at, is just release the pressure. So you put the pressure back down to atmospheric pressure, and now it turns back into a gas, and all the stuff that was dissolved in what was liquid is now just kind of easy to access, and there's no residual solvent or anything. The other way to do it is to use an organic solvent like chloroform or dichloromethane or something. Another common place would be like caffeine, removing caffeine from coffee. That's how they do that as well. Both relevant drugs, perhaps, for you guys in college. But so that's the critical point. Triple point is where you can have three phases simultaneously. These phase diagrams, if they're not super hard, so spend a little bit of time on them, and they'll make sense, and you'll get some reasonably easy points on whenever our exam is. That is it.